Welcome to this explainer. I'm so thrilled you're here today because we're going to demystify something literally all of us take for granted every single day. You turn on the tap and boom, crystal clear water just flows right out. But to get that one perfect drop of water, there's this incredible unseen world of technology, massive hidden structures, and honestly, microscopic battles happening right now at your local water treatment plant. Today, we're diving straight into exactly what filters actually do at these plants. We'll take a journey from the heavy concrete foundations all the way up to the cutting-edge math that keeps our water totally safe. Okay, let's dive into this. Here is our roadmap for today. First up, how water filtration works. Second, under drains, the hidden foundation. Third, the battle of the flocks. Fourth, the flock strength model. And finally, 6 essential filter applications. Let's get to it. Section 1. How water filtration works. So to really open up the black box of water treatment, we've got to start with something called media filtration. Basically, it's a granular depth filtration process. It uses layers of carefully selected materials. Usually you've got anthracite coal on top, followed by finer silica sand, and then some supporting gravel at the very bottom. As gravity just pulls raw surface water downward through all these layers, the media catches the suspended solids, the dirt, the turbidity, and the result? Beautiful, clean water. Looking right here at this cross-section of a rapid gravity filter, you can see exactly how it works. See that blue water entering at the top and flowing downwards? It permeates right through that beige filter media layer, making its way down into the support gravel. Now, that gravel is absolutely crucial. It's actually highly pure silicon dioxide, and it structurally supports all the fine sand above it, making sure that sand doesn't just get washed away into the drainage system below. Finally, the clean water exits through the very bottom. That bottom layer is the magic that transforms raw, muddy surface water into the totally safe drinking water flowing from your tap. Moving right along, Section 2, under drains, the hidden foundation. Now, the physical, completely unsung heroes of this whole process live literally on the concrete floor of the filter tank. On the left, we've got a real-world look at these specialized nozzles laid out across this massive concrete floor. And brilliantly illustrating this on the right is a 3D cutaway of what we call a monolithic filter underdrain. You can really just think of this like the foundation of a skyscraper. It's a reinforced concrete structure cast directly into the walls and floor. It's physically holding up thousands of pounds of gravel, sand, and water. Some of these monolithic designs, like the Centurion model, for example, they both literally decades of operation without a single structural failure. Pretty amazing, right? But here's the thing. The underdrain isn't just a heavy, static floor. It actually lives a dual life. During the filtration phase, its job is to ensure the uniform collection of treated water. It stops the water from channeling and creates this perfectly even flow across the whole bed. But as you might guess, eventually that filter gets clogged up with dirt, and that brings us to the backwash phase. Suddenly, the underdrain has to act completely in reverse. It transforms into a highly pressurized distribution network, blasting air and water back up through those nozzles to expand and clean out the filter media. It flushes out the trapped dirt without losing the precious sand and gravel. It is just a brilliant piece of hydraulic engineering. All right, Section 3, the battle of the flocks. So you might be wondering, what happens when all that physical hardware is working perfectly, but the water chemistry suddenly goes haywire? I mean, in a massive multi-million-gallon treatment plant, how do we actually know if a filter is secretly failing before it's way too late? Well, researchers in Australia at the Nepean water filtration plant faced this exact terrifying problem. Extreme weather events and massive heavy rains were causing a huge spike in organic matter in their source water. To capture this junk, plants use chemicals to bind the dirt together into little clumps called flocks. But because of the extreme weather, they were getting weak flocks, these really fragile chemical clumps with super loose structures. And weak flocks? They lead to a massive operational disaster known as turbidity breakthrough. As the water pushes down through the sand, the sheer physical stress literally rips these weak flocks right apart. And when they break, sudden, nasty spikes of dirty, turbid water break right through the filter. When this happens, a filter's runtime is absolutely slashed. Instead of running efficiently for over 40 hours, the filter just chokes in under 20 hours and needs an immediate, super costly backwash. Not good. Which brings us to Section 4, the flock strength model. So to fix this, the researchers at the Nepean plant had this absolute light bulb moment. They realized, hey, we don't need to take water out of the plant to test it in some separate lab. The filter itself is the laboratory. As the filter clogs up, its resistance to water flow, which engineers call head loss, naturally increases.
This head loss perfectly equals the shear force that's tearing at those flocks. So the head loss of the filter at the exact moment the flocks break, that is the mathematical equivalent of their internal bonding energy. It's a real-time surrogate measure of flock strength.
So the absolutely crucial point we need to focus on is this number right here, 0 NTU per day. NTU is just a standard measure for water cloudiness. By plotting the change in turbidity over time, they created what's called a turbidity breakthrough slope. A slope of 0, that means the filtered water is staying perfectly clean. It represents incredibly strong flocks that literally never break, even under the maximum pressure building up inside the filter media. Now, what's really interesting about this slide is seeing this applied in the real world. The comparison is just striking. When that slope hits 1.0, it means you've got weak flocks breaking at just 0.57 meters of head loss, and your filter, it's going to crash in under 20 hours. But if you have strong flocks, your slope is 0. They can withstand a massive 2.2 meters of head loss, and your filter hums along beautifully for over 40 hours. This flock strength model acts exactly like an EKG heartbeat monitor, but for the filter. Integrated right into the plant software, it lets the operators dynamically fix their chemical doses in real time, totally saving the filter before it ever has a chance to break.
Okay, final stretch. Section 5. 6 essential filter applications.
Zooming out from the microscopic math to look at the massive real-world impact, these under-drain filter systems are quietly maintaining consistent water quality everywhere. 1, they're treating the municipal drinking water flowing right to our homes. 2, they polish off wastewater in tertiary treatment stages to meet really strict environmental limits. 3, they protect boilers and cooling systems in industrial process water for huge factories. 4, they act as critical pretreatment in giant desalination plants, shielding those supersensitive reverse osmosis membranes from ocean silt. 5, they manage urban stormwater runoff. And 6, their compact designs are even tucked away in the mechanical rooms of specialized commercial systems, like the ones you'd find in hospitals and data centers. They are literally everywhere. And honestly, it all leads to this: beautiful, pristine, crystal clear water. We achieve this result because of a perfect, seamless marriage of engineering and science. It takes the physical perfection of high-performance underdrains distributing water uniformly, combined with the chemical precision of the flock strength model, actively monitoring the health of the filter media. Together, those two things absolutely guarantee this pristine end result. Which leaves me with this final, provocative thought for you. Next time you turn on the tap to fill your glass, are you going to picture the invisible architecture of concrete underdrains and the microscopic battles of flock strength that are delivering that crystal clear drop? I certainly hope so. Thank you so much for joining me on this explainer today. Keep asking questions, keep looking deeper into the hidden systems all around us, and I will catch you next time.